Okay, hi everyone. I'm going to talk to you today about a specific type of Android Heisenbug. This is one that we found to be particularly pernicious. It's, you have a user who finds some sequence of actions in their application that results in a crash. This crash report gets sent to the developer. The developer can try to reproduce the sequence of events, but due to the non-determinism, it's very difficult to actually get the crash to happen. So what's going on here? If you look at the code of an Android application, it's implemented with a set of callbacks. This set of callbacks is invoked by the Android framework in response to events such as showing a confirmation dialog. And so these callbacks are invoked on specific instances of application objects that are there to respond to these events. So why is this bug easy to miss? You have the stack trace, you have the location of where it occurred, and you know that there's this method, execute, that can't be called twice on the same object. So in this case, the crash is due to this onClick being called twice. However, there's another method, finish, which is supposed to dismiss the whole screen. And if you look earlier, the button is on that screen. So if you take reasonable assumptions that a developer might have, this application looks like it should be correct. So what's going on here? Developers understand callbacks in a number of ways. But if you look at the documentation, the first thing that they see is a lifecycle. This is an automata of callbacks that are possible on a specific object, such as an activity. But this doesn't include the button. The button is grabbed from the activity and registered. And so there are extended life cycles that will attempt to put this onClick into the active state of the activity. And we kind of refer to this as lifecycle plus. But this still doesn't really capture the extra stuff that we need, how finish affects the system. And so can we actually extend this lifecycle to include finish behavior? If you look at the documentation, it implies that finish will cause the pause and then a destroy, which is equivalent to getting rid of this current screen that you're looking at. But you can't actually put it here. This isn't the real behavior of the framework. And if you try to start drawing all the edges that are related to finish, this gets very complicated very quickly. So modeling finish in this way becomes really error-prone and potentially imprecise if you just try to add all the edges. So similar to an application developer, a program analysis must model the framework. And in several papers, Flow-Droid, Hopper, and more, we see that these models exist. Specifically, this lifecycle plus is with the onClick listener attached to this active state is something that we see pretty regularly. However, every blue method in this little sample application that I've shown you can affect the callback ordering in some way or another, and is something that, in order to capture these event-related problems, we need to understand. So how can we develop a precise model that accounts for all of this? So we get into the contributions of this paper. First, we talk about lambda life, which lets us build a concrete model of the internal state of how the framework is behaving. And this is based on the interface between the application and the framework. Lifestate's a modeling language that lets us instantiate that model with the behavior of a specific system, such as Android. And lifestate validation, which is a way to determine the correctness of these models beyond just it looks the same as the documentation. And then Verivita is our tool for verifying the absence of these bugs based on runtime traces. So we'll first talk about lambda life. So we have two components in this system. We have the application and we have the framework that are communicating. Some event happens in the real world that causes this confirmation dialog to be shown. The framework will invoke a callback on the application, transferring control flow. The application, in turn, will invoke a couple of methods on the framework that we call callins to affect the state of the framework. Then the user might click on a button, which invokes another callback, the onClick. But this onClick can't happen unless we have previously seen a method onClickListener in the previous callback. But at this point, it's still possible to get another onClick, which crashes the application. So this allows us to see this interaction between the application and the framework and see how the application's actions affect the callback state. Going into more detail, we can understand this based on a set of enabled callbacks and disallowed callins. We start with an onResume callback that's enabled. We can select one of these enabled callbacks non-deterministically and invoke it. As a result of this, we get the onClick that is enabled due to the set onClickListener. That can be selected from that enabled set. And at this point, the execute is called. And the property is that it can't be called twice, so we add it to this disallowed set. But onClick is still in the enabled set, so we know that the next step here can be a crash. And so the bug is that this finish somehow doesn't affect the state of the framework in a way that removes onClick from this enabled set. So one possible fix is to add another call set enable false. If you've seen the gray buttons that you can't click on a user interface, that's what that does. And that actually does prevent the click and removes it from the enabled set. And so with this state, we know that the next step that the framework is going to take will be safe. So the next thing that we're going to look at is we've talked about these enabled and allowed sets, but how do we write down a specification that lets us compute what the next set of enabled callbacks or disallowed callins could be? And so we do this based on the history of the interactions between the application and the framework. So the first rule that we might write is that set onClickListener enables onClick, and we write this with a little arrow. And that updates the state to have that onClick enabled in there. We can write what are called disallow rules that match that this execute has occurred and remove it from the disallowed state. And then we can also write a disable rule which matches that the set enable false has been called and removes the onClick. So this provides a concise way of specifying the effects of some history of execution to update what we think could happen next. So once we write these models down, it's very easy to assume something is true which actually isn't. In the example that I showed, we had the fact that the developer might have thought that this finish prevented it on click. This first rule, oops, what just happened there? Sorry about that, everyone. Okay, this first rule that we write actually states this assumption that finish will disable the onClick. The second rule states another assumption that we have that set enable false will do the same. And so at this point, we don't actually know which of these two rules is correct and which one isn't. So in our experiments, we collected over 2,000 traces that we can check this behavior on. And what we find is that there are traces that are direct counterexamples to this specified rule that click doesn't occur. We match this findViewGuy to connect the activity that the finish is invoked on in the button, and then we connect the finish. And so this trace can be from a completely different application, but it shows the same sort of pattern, and it shows that a on-click is possible. So we can say that this rule is unsound. With set enable false, we can do the same experiment and we don't find a counterexample. And so what this allows us to do is develop a model. As we develop the model, we can search for these counterexamples and only admit rules that are correct. Next we'll talk about Verivita, which is how we actually use the Lifestate spec. So if we take a trace, we can consider each of these callbacks some transition. And our tool, Verivita, takes this set of transitions and a Lifestate model. And we explore all of the possible ways to replicate, remove, and reorder the events in the trace. And then we can ask, is it possible that this system reaches some kind of crash? And if it cannot, in the case of using set enable false, then we say that the trace has been proven and that we cannot rearrange it to find one of these event-driven defects. So moving on to actually evaluating the system, we first ask the research question, are Lifestate models actually necessary for precise protocol verification? And with the experimental setup, we start by recording a bunch of traces. We started out with 5 hand-selected real apps that were suggested to end Android developers. These are open source things. And then we had an actual device set up, and we had somebody run it for 10 minutes for each trace, generating 50 traces. Then we created a much larger set where we had 121 apps that were automatically driven with a tool that effectively just spams clicks and button presses and stuff on the screen. And with this one, we created over 2,000 traces. We compare 4 different models. First is Lifestate. Is that flickering? Oh, I guess that's the light. We compare 4 different models. First is Lifestate, which is our hand-developed model that was validated on all of these traces as we went through and created it. Then we have a top model, which is any callback at any time. And this allows us to kind of see the effect of not having any ordering constraints on the model at all. Lifecycle only puts constraints between callbacks. And so this is sort of like the documentation in the Android developer docs that doesn't have the on-click attached. And then we show Lifecycle++, which is this the standard model without validation to see how well it does. So we're going to compare the number of correct traces proven by each model. And we start by going through community discussions and finding these methods that have the same sort of behavior like execute, where there's some state behind it that can cause a crash. We then filter all of the traces that we got for which ones actually use this method. So there's 102 total, but we have an individual number for each of these. We look at the number of traces that are verifiable, which means that they don't contain a real defect, because several of the applications did misuse these. Then we look at the top model, which proves about 22%. the lifecycle model, which proves about 27%. The lifecycle plus proves about 57%. And the lifestate model proves 83%. So to compare it with a larger set of traces, we notice that the baseline increases a fair amount. We suspect that this is due to the automatic tracing not getting as deep into the app as an actual user. But Lifestate still improves on these baselines. So the final research question is validation necessary to avoid unsound callback control flow models? And so for this, we took all of the traces that we gathered in the previous experiments. With Lifestate, we developed this model while doing this validation and checking that we're not admitting rules that are unsound. And so we validate on 99.9% of these traces in that case. With Lifecycle++, that's the standard model that's implemented without validation. And we referenced the Flow-Droid implementation of this to make something that was kind of realistic about what you would do if you were trying really hard to make something that's good without having this extra check. What we found was that the lifecycle doesn't validate on 58% of the traces. And the other kind of surprising finding is that the vast majority of these are blocked within the first 25 steps of the trace. And so what we find is that it's incredibly hard to make a correct model of the Android framework without some kind of automated check like this. So in conclusion, we looked at this callback control flow problem, and we got this lambda life model that lets us reason about the framework in a simpler way. And then we created this specification that focuses on the application framework to allow, so I guess that's out of my time. So, thank you, everyone.
Thanks very much, Shawn. That was wonderful. Do we have any questions from the audience?
I saw one in the back there.
So one thing you mentioned at the beginning of the talk was that like drawing a sort of a correct transition system was really led to a very, very complicated graph. Mm-hmm. And now that you have one of these validated models, like how will you, if you wanted to present the model to a developer, how would you do that?
So that's actually a very, very good point, that if I could show this model to a developer, it would probably significantly help them because the system is so complicated. I think that that's a little bit of a task for future work, but you can look at the implementation of the Lifestate rules and get a sense for what might be going on. I would say they're a little bit easier to understand than the actual source code of the Android framework, because a lot of these callbacks are triggered by operating system stuff. So,
any more questions?
There's one in the front here.
So you showed one kind of rule when you have a set of events, and then it should not trigger something else. What are the other sorts of rules that you can encode in the Lifestate model?
Oh, yeah. So we have a rule that says this action has enabled a callback based on the history. One that says this is so the enable says a callback can happen. That callback can happen in the future. Disable says it cannot happen in the future. And then we have a set of mirrored rules for allow and disallow. We have one that says you can now call this method on the framework, which is the allow, and one that says you now cannot call it on the framework, which is a disallow. And so those are the 4 types of rules that we encode.
Wonderful. Okay, thanks very much, Shawn. Let's thank our speaker again.